Hello everyone. In this video, we're going to cover the topics from lessons in week 8 of the course. If you open up the course schedule, you'll see that week 8 is our last week of our algorithm analysis module. However, we're not going to finish our discussion of algorithm analysis here. For the remaining weeks, when we talk about data structures related to trees and graphs, we will still be discussing the time complexity of these implementations in order to evaluate their efficiency. This week, we're going to talk about hashing, hash functions, and implement a hash table and a map abstract data type. The reading for this week is Miller and Raynham, section 5.5, and the participation activities in SciBooks chapter 3, as well as programming assignment 4, and I will talk about PA4 in a separate video. Let's get started with lesson 8-1, an overview of hashing. Learner objectives for this lesson: understand hash tables and their associated hash functions, and learn how to handle collisions in our hash tables with two approaches. One is linear probing and the second is chaining. So to motivate talking about hashing, let's review what we know about searching. When we search a list or array, we're looking for something that maybe is stored in that list or array. And we know two main algorithms for searching for an item in a list. Linear search can find an item in linear time, and binary search can find an item in logarithmic time. The stipulation for binary search is the list must be sorted. There's another searching technique called hashing that can support linear time for searching. Hashing typically sacrifices space in order to improve time complexity, and it does this by utilizing information about where an item should be in order to look up the item's location, i.e., to search for it. By definition, a hash table is a collection of items that are stored to make it easier to find those items later. We've actually already seen hashing in action when we've been working with Python dictionaries. We know that a dictionary is a list with keys as indices, and those keys don't have to be integers like they do in lists where we're looking up positions. A hash table can also be called a dictionary, a map, a lookup table, or an associative array. In general, we think about hash tables, dictionaries, maps, etc. as implementing a map abstract data type. We'll cover more on the map abstract data type in a little bit. So let's think of a hash table and a dictionary as a map. We've already been trained to do this in terms of dictionaries, but now we have this new concept of a hash table. A dictionary maps a key to a value, meaning that there's a function f, some function, such that when f takes a key as input, it produces a value. We see this with our key value pairs in a dictionary. Now, a hash table uses this special function f to compute the location of a value by using the value itself as the key, instead of storing the keys in the table. F is called the hash function of the hash table, and it maps values to their locations in memory. It always helps to motivate with an example. So let's take a look at the following hash table that has 11 slots or 11 positions. You can think of this hash table as a one-dimensional list of 11 locations, 11 slots to store items. So initially, we have this one-dimensional hash table. There are 11 slots or buckets in it. And right now, I have none to let you know that each one of these buckets or each one of these slots is empty. It doesn't store anything. Each slot can hold an item, and each slot is indexed by an integer value starting at 0. To determine the mapping between an item and the slot where an item belongs in the hash table, we will use a hash function such that f accepts an integer item, and it will produce a mapping to a slot location. The hash function we're going to use will return an integer representing a slot, and that integer is going to be restricted to the available slots in our 11 item list which is 0 to 11 minus 1, which is 10. Let m be the size of our hash table. A simple hash function that we're going to use for now is called the remainder method. So the remainder method uses mod to determine the slot or the location of an item. So suppose we want to insert the value 42 into our hash table. So we want to store 42. Since the size of our hash table m is 11, if we compute the remainder method for the item 42, f of 42 is going to be 42 mod m. M is the size of our hash table, which will give us 9. So essentially what's happening here is we're going to map any integer to a slot in this table by modding by the size of the table. So we'll place 42 at slot number 9. So here's an updated view of our table here, and we see at slot number 9, 42 is now stored. So for a few more examples, let's insert 22, 7, 16, and 90 in that order into our table. So f of 22 is 0, because 22 mod 11 has remainder 0. So we place 22 at slot 0. Now there are 2 slots filled in our table. Next we'll insert 7. 7 mod 11 is 7, so 7 stores 7. 16 mod 11 is 5, so 5 stores 16. And lastly, let's insert 90. 90 mod 11 is 2, so now at position 2, 90 is stored. Now 5 of the 11 slots are occupied. The number of slots filled compared to how many slots are available is called the load factor of the hash table, and it's commonly denoted by lambda, which is equivalent to the proportion of slots filled. Number of items divided by total slots, or the size of the hash table. So right now, 5 of our 11 slots are filled, so our load factor is 5 11ths. Now that we've added some items to our hash table, suppose we want to search for an item. When we want to search for an item, we're going to use the same hash function f that we use to insert items into our hash table to look up if items are in our hash table. Since a constant amount of time is required to compute the hash value, that's our remainder method, and then index into the hash table at that location, this searching operation is big O of 1, it is constant time complexity. If everything is where it should be, we have found a constant time search algorithm. But let's think about this last part. Will everything always be where it should be? Do you see any potential problems with this approach? Let's take a look at yet another example. So suppose in our running example, we want to insert 35 into the hash table. So 35 mod 11 is 2, but if we look at our hash table at slot 2, there's already an item there, item 90. So we call this a collision. When an item maps to a slot that is already filled with another item, there's a collision. So our constant time complexity approach only works when each item maps to a unique slot. So how can hash tables handle multiple items hashing to the same slot? There are 2 approaches that we're going to cover in this class for handling collisions. The first is linear probing, and the second is called chaining. So let's take a look at linear probing. We can process a collision by simply placing the item in the next available slot in a hash table. We can sequentially search by rehashing until we find an empty slot. If we reach the end of the hash table without finding a slot, we can circle our search around to the beginning of the hash table and keep looking. So in our example, when we were trying to insert the item 35 into our hash table, we mapped 35 to slot number 2, but slot number 2 was filled with 90, but the next available slot, slot number 3, was empty. So we can put 35 in slot number 3. So now we've stored 35. When we go to retrieve an item from the table, we're going to have to linearly probe to try and find the item. So let's say now we're trying to retrieve our item 35. We would start by hashing 35, just as we would normally before linear probing, and we would start at slot 2. Now, if 35 is not in slot 2, and we know a collision has occurred with this slot, perhaps because we're going to augment each one of our slots with a variable that's going to let us know if a collision has occurred here, then we know we need to start linearly probing to search sequentially until we find 35, or we have searched the entire list, or we have reached an empty location or a slot that has not received a collision. So there are a few issues with this implementation of linear probing. For example, if many collisions occur at the same slot, then the surrounding slots will be filled due to linear probing. This can cause clustering in the hash table, that is, regions of the table that are full and regions that are empty. So we want to try and have as even of a spread of items in our hash table as possible. So this is going to reduce the clustering that could occur in our hash table. So to reduce clustering and have this even spread, we can skip values when rehashing to spread out the insertion of the item from its original slot. That is, we're still going to probe to find new slots, but we're not going to find new slots immediately adjacent to our original hash location. And to address the full sequential search of an item on retrieval, as alluded to earlier, we can add a flag to each slot representing whether the slot has always been empty or if it is empty after removal. The flag helps to optimize item retrieval because we do not have to search until we reach the item or an empty slot. If the slot has always been empty, we do not need to search beyond this point. Now let's take a look at an alternative approach from linear probing called chaining, or also known as linked processing. So in chaining, each slot in the hash table stores a chain of items. In this manner, a single slot can store many items. When an item maps to an already occupied slot, meaning a collision has occurred, the item is added to a linked list whose head is stored at that slot. So let's return back to our example, and let's assume that the start of our example is going to have a current state of our hash table that looks like this. So we're going to insert 35, which maps to slot 2, but we know that slot 2 already stores item 90. So in linear probing, we would insert 35 at the next available slot, or perhaps skip some values to prevent clustering. But in chaining, we're going to instead insert 35 into a linked list with 90 at the head. So I've changed the orientation of our hash table so that in Markdown, I can show this linked list as kind of a jagged list associated with our slots. So as our linked lists are going to grow, our rows are going to grow to the right. So to summarize, slot number 2 has a 2-item linked list. At the head is 90 and at the tail is 35. As another example, let's add 2. 2 mod 11 is 2. 2 is full. It stores the linked list 90 and 35. So we insert 2, item 2, at slot number 2's linked list at the end, the tail. Now, when we go to retrieve an item from our hash table, we're going to compute the slot via a hash function, just like normal. And if there is a linked list at this slot, we need to traverse that linked list until we either find the item or reach the end. If we reach the end, we know that this item is not in the hash table. Now, we want to try and keep this list of items, our linked list, as short as possible. If we start to have clustering occur, then we'll have a lot of empty slots, but some slots that will have quite long linked lists, which is going to kill our constant time complexity search and retrieval algorithm. So let's take a look at the time complexity of hashing. And we need to return back to the load factor lambda, which is the number of items filled in the hash table over the total number of slots in the hash table. So if lambda is small, meaning our table is fairly open, it's sparse, there will be a lower chance of collisions occurring. On the contrary, if lambda is large, meaning the table is fairly full, there will be a higher chance of collisions occurring. The more collisions there are, the less efficient item placement and retrieval will be. And this makes sense because we'll have to perform sequential searching in linear probing and in chaining. So our analysis for linear probing, successful retrieval, the average number of comparisons is 1/2 times 1 plus 1 over 1 minus lambda. For unsuccessful retrieving using linear probing, the average number of comparisons is the same except for squaring our 1 over 1 minus lambda term. For chaining, successful retrieval, the number of comparisons is 1 plus lambda over 2. For unsuccessful retrieval using linear probing, the average number of comparisons is lambda. Now, I have some practice problems listed here that I encourage you to work through for practice. For example, on this first one, I have a city, which I've given a somewhat arbitrary hash code, and I want you to compute the slots that this city with this hash code would map to using the remainder method for sizes of the hash tables 5, 7, and 13. In this case, use linear probing to handle collisions. And in the next problem, instead of using linear probing, use chaining and see how the two tables compare.